Welcome, Dr. George Sergi. So, today we have Dr. George Sergi from Vector Corrosion Technologies. He is a pioneering figure in cathodic protection of concrete structures. Significant experience in this area of about 20 years. So, it's my pleasure to actually have an interview with him. On what is the development, what have been happening in this area, and what we should do in future to protect most of our concrete structures. So welcome, sir, for
thank you very much,
valuable time.
Thank you for giving me the opportunity to talk to you.
We all know that that you have been developing many systems for cathodic protection of concrete structures. Could you please tell something about how you started working in this area, or what motivated you to get into this industry like 30 years ago? At that time, how was the industry and what made you to get into this, and then little bit story of early time.
I'm pleased that you said 30 years because it was actually in the year of 40 years now.
Okay.
Yes, I mean, it was kind of accidental in a way because I had completed my studies on metallurgy, material science, and I finished a master's degree on corrosion. And out of the blue, I got an invitation by one of the professors who were working on corrosion of steel or concrete at the time. And he asked me whether I wanted to do a piece of work for him as a research on galvanized steel in concrete, the behavior of galvanized steel. Because galvanized steel is just a coating of zinc on the steel. Mm-hmm. And that gave me an opportunity to understand how zinc works in a concrete environment. We were trying to see whether galvanized steel could last sufficiently in a concrete environment. And what we did find by playing around with different solutions and different mixtures, that as you increase the pH, zinc was corroding more and more. So that was the first lesson that we learned, that in fact zinc could be very, very active in a very highly alkaline environment. Subsequently, again, out of the blue came the idea that they wanted to use cathodic protection that was used in America, not fantastically successfully, but there was a new process that was being adopted for steel reinforced concrete, and there was a real need in the area that I was living in, near the university, to carry out some trials to identify types of anoding material that could work for cathodic protection in reinforced concrete. And I was just lucky to be in the right place at the right time. The trials were about 3 miles from our university, so we became the main body of overlooking these trials, and we did some experimental work also to learn about the side effects of cathodic protection. So all that build-up of knowledge obviously attracted me to
remain in that area.
To remain in the area, and just one thing led to the other. We had an invitation from a local company, a repair production company, who were telling us that the patch repairs were failing, even though they were working so hard to improve their materials. What is the reason, and so on. And so we understood
the halo effect,
the concept of the hollow effect and the halo effect and the incipient anode formation.
Okay.
And then we were asked to solve that problem. And the rest is history, really.
Rest is history. Any other major milestones which, in the develop, because Vector has several products in the market, or not necessarily Correct. This particular company, but there are several products in the market. So how different products evolved, if you can give some light on that.
Yes, I think, again, it all started at that trial in the UK, where they were desperate really to find some anode materials that would actually work. And there were a lot that were tried there. I would say that 80% of them had failed. They weren't producing enough current. They were giving other problems like acidification around the surface of the concrete, or direct failure, like some of the paint systems would flake off after a while. And at that time, only two systems actually stood out. There was a particular paint system which was based on carbon, and a mesh that was titanium based and was coated with a mixed metal oxide to allow better conductivity. But from there, of course, once cathodic protection became established, many people got involved. Research was carried out, and I think one of the major things was the invention of the discrete anodes, which were then able to put into drill holes into the concrete, so structural elements that were very difficult to get to because they were buried deep into the concrete.
So before that, it was all surface applied systems.
Totally surface applied. But now, they recognize that they may not have been protecting some critical points. For example, one of the critical elements in construction around the Midland Links, as we call it, just the elevated sections of the highway that goes around the city. One of the major constructions is a half joint. And a half joint has a very critical steel bar that goes across, very close to where the joint is, and that's hidden away inside the concrete. And if that fails, the whole structure could collapse. So how to protect that particular element? Well, you can only do it by drilling a hole and getting close to it.
Okay.
So that necessitated the development of the...
How to get closer to the rebar.
How to get closer to the rebar.
And to make it more effective in that way.
Correct, yes.
Also, I know you have done a lot of lab research and product development. Whenever we try to do something new to the market, there will always be some resistance.
Absolutely.
So what are the different types? Because we are also in India, this is something new to many of us. This technology is, many of the engineers don't know about this technology, and we have a lot of structures which are either experiencing corrosion, but we don't know that. So we are waiting, to see more corrosion-related damage and issues like that. So, but still there is a lot of resistance when it comes to new technology to be implemented. So how, maybe you might have also faced something similar, and how you could actually overcome such scenario.
I think that is a very true case. In the UK, everything goes through the Highways Agency, or what is now called Highways England. And if they make a decision to use a system, then it comes out into the market.
Mm-hmm.
Before that happens, you'll be lucky if you persuade one or two engineers to use it, because they're all waiting for the Highways Agency to.
So you're waiting for the codes and the direction from the government.
Correct.
It has to be in some book.
That's right.
To be able to use.
That's absolutely right. And there was, the fact that they had a big problem with the Midland Links meant that they had to do something about it, and they basically reached a stage where it was now, they had to do it now, otherwise they would start having to demolish the structures, and that would have cost a huge amount of money. So maintaining those structures was so important to them that they were happy to carry out these trials.
Okay.
And that gave the opportunity for the cathodic protection industry to develop from that. Later on, when we introduced galvanic anodes, Highways Agency were not interested.
Okay, not interested.
Well, we already have a solution. Why should we bother with anything else? And that was a very hard work to try and convince the Highways Agency to adopt galvanic anodes, and it probably took about 10 years for them to consider that actually putting it in patch repairs may be a good solution. And it took a lot of visits to the Highways Agency and explaining and showing results, and it had to wait for some results to occur. And as I showed to you, we had a 20-year history of galvanic anodes being introduced.
So that's
in
the same challenge which we also face when we try to suggest new ideas. We are asked to give data.
Correct.
And not short-term laboratory data, but the long-term field data.
Correct.
So
but
when we don't have it,
I think that you could be at a better advantage that we were, because
because now we have your results.
There are results that are available from the UK, from other European countries, and when you have that at hand, hopefully it will be a bit easier to persuade the powers to be, the people that make the decisions, that if they're using it and it's good enough for them, surely it can work for India as well.
Okay. And now I know there were some companies in India also where they were having both repair material wing and cathodic protection wing. But unfortunately, because there was a perception that these two wings are going to be competitors,
right?
Because the repair material industry and cathodic protection industry. So, what is your opinion on that? Do they need to be, or are they really competitors, or they are actually helping each other? In other words, if you have a structure which is repaired without cathodic protection system and repaired with cathodic protection system, the second case you may see that the repair is actually going to be durable. But many don't realize that, then they look at it as a competitor and then tend not to use cathodic protection. So what's your opinion on that? Are they really a competitors, or they are helping each other?
Absolutely no competition, because it's two different things. A patch repair is a patch repair, and you can apply a patch repair and it would last for a few years, not because the materials are bad, but because of the halo effect that I mentioned before. You apply fresh repair to an area that you've taken away the old concrete, you've cleaned the steel, automatically you're making that the cathode of the system, and somewhere else there has to appear an anode to balance it out, and that tends to happen around the edges, which is the nearest to the patch, where there's probably still a little bit of contamination. It wasn't a problem beforehand because that patch was corroding so much, it was kind of protecting the outside. But now the roles are reversed, and therefore corrosion will start in the periphery. Now, no matter how good your repair is, no matter how good your repair material is, you cannot avoid that.
The interface between the old and new concrete, the steel there will...
And it doesn't even have to be as a repair. You may want to construct another extension to your old structure. The same would apply there. You've got nice fresh steel
in contact with the old
concrete, in contact with the old, and the same kind of effect will happen. So all the galvanic anodes will do, if you were to use galvanic anodes within the patch repair, is prevent that problem. So what is the issue? Your patch repair would look better, it would last longer. So obviously the two should be working together, I believe.
Okay. Now one other question which we have is, again, it's all about the perception, that people try to borrow ideas from one industry to the other. So like in this cathodic protection also, people think like some of the codes, existing codes, they were originally made for steel structures or structures without concrete elements or metallic structures. And we are adopting those criterion which are good for those structures maybe sometimes with aqueous environment, but when it comes to concrete, it's a whole different ball game. But still we try to use the same code. So what do you think that we in the concrete industry should do to work on modifying the codes and making them very specific to the applications in concrete?
Well,
Different, what are the challenges? Or
I think that sort of process has sort of been going on in Europe and in America with the European standard and the NACE standards, which tries to concentrate on the specifics of steel reinforced concrete. Or in fact, I think it contains masonry as well, but they've recognized that it's
steel versus a ceramic in contact.
Yeah. They recognize that there's a difference between steel underground, for example, and steel above ground structures. And the specific code of practice or standard that only deals with structures that are exposed to the atmosphere.
Okay.
So that is a specific condition, specific way of looking at the problems that you will face if you're trying to apply cathodic protection. The biggest issues are the resistivity of the concrete, because it's above ground, it can dry easily, you can get wet-dry cycles, or you can get variations in current. Other issues may be the type of anode that you use, that it's got to be durable, it's got to last 50 years, 100 years, whatever the design life of your system might be. And also the spacing. The spacing is a big difference between what you would get in a structure above ground and in a structure below ground. Below ground, because of the low resistivity, you can space anodes quite widely apart. And in fact, in pipeline cathodic protection systems, you're talking about several
meters,
well, even kilometers maybe, where you've got anodes spaced out quite widely, yet they still protect the structure because there's such low resistivity. Current can flow everywhere. You cannot do that in concrete. The spacing really needs to be less than half a meter in most cases, or even less, depending on the resistivity of the concrete, because the throw of the current becomes much more
but that's
difficult.
One area where we still don't have a rational design methodology considering these different factors and then come up with a design design methodology for cathodic protection systems for concrete structures, right? Do we have?
Yes, I was talking about the European standard, which is
about to come.
It's been in existence, but there's now a review over the next year and a half, and that it's necessary to have these reviews, and it's been happening every couple of years so far, but we still haven't got it right. And the issues are that different people have different viewpoints, and it's so hard to get a common standpoint. But even so, those standards are actually quite good at the moment, and I would recommend that as a starting point, you go with what's already available in those standards.
Now coming to this, we talked about conventionally reinforced concrete structure. Now there's a new set of pre-stressed concrete. A lot of new structures are built with pre-stressed concrete elements. And if there is corrosion, we recently did some study. We found that the corrosion will happen, but it won't show stains on the concrete surface, rust stains. So it takes longer to detect. So basically you will think that nothing wrong is going on, but it's actually corroding. So hidden corrosion is happening. So in such cases, for pre-stressed concrete, do you think that cathodic protection will be a good thing to do, especially for new structures, so that we can ensure that they don't corrode? Or what are the challenges when we try to do that?
I think there are many challenges.
Yes.
You can't just take the one and move it on to the other. Unfortunately, in a lot of cases, you would have a sheath that surrounds the strands, for example, and you cannot pass current through the sheath. So, sort of future generations, if we start thinking about it, then do we make that sheath conductive perhaps, and we allow the current to go through, or do we pre-design so that there's an anode material, or the sheath itself could itself be an anode material, so we can subsequently, if we need to, or even from the beginning, apply a current to the.
So when you said the sheath itself could be an anodic material. Earlier we used to have GI pipes or galvanized iron pipes as the ducts.
Yep.
But
Well,
now we use plastic HDPE pipes.
Correct, and obviously that's sort of taking it a little bit backwards because there's no way you can neither pass current through it.
So are you suggesting that we should actually go for metallic ducts and not the plastic ducts?
It's something that we should be considering. I think we need to have a long-term view of these things and look at what the problem has been so far. The biggest problem was that, as you explained, there's corrosion happening inside, and you don't know that.
You don't know that.
You have no idea. You can't see it. There's no staining, so even if there's a lot of corrosion, the only way that you find out is when the thing breaks.
They snap.
And they snap. It's too late.
It's too late.
So, the people are finding such a lot of difficulty now in trying to stop that corrosion, and really the only way is if you try and insert some non-corrosive material or some protective material through the strands themselves. You have to inject it from one end and hope that it covers the steel reinforcement and at least holds it in that position so there's no further corrosion. So to apply cathodic protection, I would say is almost impossible unless the strands are exposed inside the concrete. Then you can apply a low level of cathodic protection, because the other element of, I was going to say dispute, but it's not really a dispute. If you introduce hydrogen evolution on the steel surface, which can happen if the potential of the steel goes below minus 850, i.e. when there's low oxygen availability or what have you, that can cause hydrogen embrittlement. It's a case for galvanic anodes, a good case for galvanic anodes, because they would never allow the potential to drop that low. But it can only work if the sheaths are not surrounded by a non-conducting material. So I think, looking into the future, it's just a suggestion, obviously, why not make the sheaths out of material that can apply a current directly to
and it's very close to the strand.
And it's very close. It's going to be a very low current density because of the low resistivity.
Okay, that's a nice idea to try.
It's an idea for you to work on. Research.
So, what other things do you think we should work on? For the next generation engineers to work on. What's remaining?
I think the standard itself is actually in need of improving, in my opinion. That it's not a common opinion, so I may have difficulty in trying to persuade the others in doing that. One of my main issues is the 100 millivolt depolarization criterion, which everybody seems to want to use. It's been in the standards for a number of years now, and it's both in the European and the NAE standard. But 100 millivolt depolarization, we have found that it's not totally meaningless. It means that you are reducing the corrosion rate by possibly a factor of 10, which is a very good start. But often there are cases, particularly with galvanic anodes, where you can't get 100 millivolt depolarization, or certainly you can't get it all the time. You can get it in certain periods, sometimes you don't. And that almost disqualifies the galvanic anode cathodic protection from being recognized as a cathodic protection
only impressed
system.
Current technique will.
Yeah, so in that case, the impressed current techniques can do it. They can turn on the current. But do you need that extra current? We found that with lower than 100 millivolt depolarization, we can retain the corrosion in a lot of cases. Okay, sometimes you may need to go to impressed current cathodic protection for different considerations. But if it's a small area, particularly, and by small, it could be up to 10 meters squared, 20 meters squared, actually going through the cost of installing an impressed current cathodic protection is really not a good suggestion for the client, because they get this initial cost of having to produce the whole system, including the
and then monitoring and making
and then
sure
monitoring
that they are
every year, and they have to achieve this 100 millivolt depolarization.
and also
all the
ensuring
time.
that the system actually vandalism and many other
For sure,
on-site problems.
because there's a lot of outside wires and so on. But those sort of areas, they can easily be coped with galvanic anodes, provided you can design for the right parameters, the right spacing to achieve the current density that you require. Depolarization may not be 100 millivolts, maybe 80, sometimes 120, sometimes 60. Does that mean that the thing is not working? Well, we have found that, in fact, because of the variation of the current, the fact that sometimes you get a lower depolarization, all that it means is that at that particular time the current density was a bit lower because the concrete was a bit drier. Now, if the concrete is a bit drier, the steel is not corroding as much, so it doesn't need so much current. So there's a lot to be learned from
multiple
that.
factors have to be brought in before we decide on this
Absolutely.
criteria.
And I think that using the depolarization in a different way would help us tremendously. We can use a combination of depolarization and depolarized potential and current density. That gives you an idea of what your corrosion current density is, so how much the steel is corroding. And if you use it in combination with the depolarized potential, it also tells you how much corrosion is going on. That should be a better criterion, a better set of criteria than just the 100 millivolt depolarization.
And especially with this new type of concretes like highly resistive concrete and low alkali concrete, so we may have different challenges also to do research on.
I believe so. I think there's one thing that we've sort of taken for granted is that all the concrete is made of Portland cement, and it's got loads of calcium hydroxide, which saturates the solution and keeps the pH at a certain minimum level, and that acts as a buffer in actual fact for protecting the steel reinforcement to produce the oxide film, protective oxide film. But there's now a different way of we should be looking at it, because that calcium hydroxide is gradually being removed because of these new materials that are being used. Even using substitute materials like slag or microsilica. I know that if you add enough microsilica, you can drop the pH down to even 11, and that's a totally different environment for the steel reinforcement. So the corrosivity would increase with these types of cements. So we need to be looking into that really early on, because what I imagine would happen is that we are satisfied ourselves that these concretes are durable and they're strong, and we start using them, and then we find that 5 years later the steel is corroding, and we start asking the questions then. For that, let's start asking the questions now and try and design accordingly.
So with that, I think the main idea is we have to actually start having a corrosion management team in most of the construction projects.
I believe so.
Which will probably help us in preventing corrosion from happening rather than waiting and doing a corrective repair or maintenance practice.
Absolutely right.
So I think the cathodic protection will be one way of controlling corrosion in concrete structures. And like you said, we still have a long way to modify the system for the new type of concretes and work on codes, mainly adapting the existing codes for concrete application to concrete structures for conventional and pre-stress. So these are the challenges I think we have ahead of us.
There's quite a few challenges, though.
There's
a lot of research still to do.
Research to be done. Thank you very much for your valuable time.
Well, thank you very much for having me here, and
I
It's been
think
an absolute.
we cherish this time.
I have as well because, like I said to you privately, I think this is a fantastic campus, and all your students here are really lucky to be working here. Fantastic environment for the brain to be working beautifully.
Thanks to IIT Madras for providing us that environment. Thank you.
Thank you.